Amazing. Over to you, Debayu.
Yeah, thank you. So today we have two very fancy names: Infinite Descent and Vieta Jumping. So what are these? Why is this guy doing these fancy things? Well, it's not really that fancy, and I'm assuming all of you know how Pythagorean triplets work. It would be really cool if you all could like speak up all the time.
Okay.
It's like hard to look at the chat and everything. So yeah, you probably know that you can categorize the solutions to like Pythagorean triplets, something like I don't know. These like a constant, like something like this works, right?
Yeah.
And you basically can generate like infinitely many solutions because you can vary the constant d and like all of these. So there are a lot of and like this is a Diophantine equation, right? And there are a lot of Diophantine equations which have like infinitely many solutions. But a lot of them also have finitely many solutions. Sometimes you might be asked to like categorize all the solutions and everything, even if they're like infinite. And sometimes you probably just want to prove that there are a few solutions. And they probably don't even have a non-trivial solution. And by non-trivial, I mean that you will have a solution like 0, 0, 0, and yeah, that's it. Something like that. So we will start off with the problem, which is a very classic problem that is like used quite literally everywhere when you were getting introduced to infinite descent. So it's this equation basically. Wait a second. And you want to find positive, like non-negative integer solutions to this. What's a good notation for like whole numbers? Is this good?
I think the only solution here is 0, 0, 0, right?
Yes.
0, 0, 0 works. And you were claiming that the only solution is this, right?
Yes.
Yeah.
I think XYZ belongs to Z only because Z greater than 0 would obviously indicate 0, 0, 0 is the only solution.
Sure, but you will soon see why I am particularly using like whole numbers. Like just in this context, right? Okay, so I will give you a minute or like a few minutes to try this problem, and you are just feel free to uh, just think out loud, right? And tell me what ideas you have.
I mean, our aim is to prove that this is the only solution, right?
Right.
Okay.
Maybe we could take this mod 9, in which case each of the three cubes will be 0, 1 or -1, in which case the only solution would be if all of them are 0, which means all of these are divisible by 3.
Okay.
Then we could divide them by 3. And if this isn't a 0 solution, then we can find a monovariant, which will mean that
Yeah. I see what you're doing. Yeah.
X, Y, Z all are greater than equal to 0. So X cube, 2Y cube, and 4Z cube are all going to be positive. So they will never be equal to 0 only if X, Y, Z is equal to 0.
I'm sorry. Could you repeat?
X, Y, Z belong to integers greater than equal to 0. So X cube will always be positive, greater than 0. 2Y cube always be greater than equal to 0.
Sure.
4Z cube will always be greater than 0. So they can't be equal to 0. So everyone should be X, Y, Z should be equal to 0.
Wait a second. Wait a second. Yeah, I see. I see what you're saying. But okay. give me a minute, please. Okay, I'm sorry. Yeah, I'm back. Sorry for the interruption. Okay. So you were essentially doing sort of a size argument, right? And yeah, that does work. But okay, so in the chat, Dave says something. Taking x equals 2x dash, we will end up getting same type of equation. Right. And why can you take x equals 2x dash?
Because we can take like mod 2 and x cube would be 0 mod 2, so x should be 0 mod 2.
Absolutely. So x has to divide x. Is that clear? Is that clear to everyone?
Yeah.
Good. So you can write x as like 2x1. And you can essentially, as people in the chat mentioned, you get, when you rewrite this thing, you get this. And you basically have a very similar equation. You went from xyz to I don't know, y z x1. And you can repeat this argument here, right? Because this is essentially the same thing, right?
Yeah, but how did you, replace like x with 2x1? How did you identify that you had to take 2x1?
X has to be divisible by 2. So you can
Yeah.
like that.
Okay.
Does that make sense?
Yeah, it does.
And yeah, now you have this. You can repeat the same argument and you get another tuple, right?
Yes.
Now, will like all of these tuples be a finite set or will it be like infinite?
Finite, I guess.
Not really, right?
Oh
Because
no, we can take any
Still,
values
there
of
will be only
x1
one
and stuff.
position,
Yeah.
no? 0, 0, 0.
yes, because you are like these are fixed, right? Like for example, just look at this transformation. These two are
Yeah,
fixed, but x1 is like smaller than x.
right.
So each time actually the thing gets smaller.
Yeah.
And if you want to like think about it a bit more rigorously, just consider like the sum of each tuple. There's always decreasing. As someone said, you will get a monovariant. You can do this. I think someone took mod 9 and did the same thing. And yeah, so what happens is you keep on getting smaller and smaller tuples. But can this happen?
The solution will still 0, 0, 0.
Yeah, it has to be 0, 0, 0. Can someone explain why?
Because like every element should be divisible by 2 infinitely many times. So 0, 0, 0 is the only option.
Right. So basically, eventually everything gets repeated infinitely many times, which means that say VP of one of these will be like V2 of one of these will be like infinite, which is not possible, which is only possible when it's 0. Right? This is one argument, and another argument is since we're working with like non-negative integers, um, yeah, since we're working with non-negative integers, you cannot just go on forever, right? You have to stop at like zero or something. Does that make sense?
Yeah.
Okay, great. So this is basically our idea of infinite descent. Basically, you have a pair, you try to get a smaller pair or bigger pair, you prove that you can have like many such pairs, and this is just bad because of some issues going on. And yeah, sometimes like here for example, this kind of like simple because you just like this quite like this is very feasible to do, right? Like it's very easy to see that x has to be divisible by 2, so you can have this again, and the sum of thing is always decreasing. But sometimes the quantities that you need to consider are sort of non-trivial, so we will obviously do a problem. This I'm actually not aware of what the source of this problem is. Even if okay, I will try to like uh, notify you the thing later. Wait, what is happening? Wait, I need to copy the problem for some. Sorry, people, give me a minute. Okay, I can just take a screenshot. There. So you have very fancy names here. Finnicle the fairy finds a solution to this equation and everything. This problem actually, back in 2021, there was a math Olympiad camp, which was conducted by a lot of our seniors, like Rohan Veya, and others. And there was like a team contest in that camp, and this was one of the problems there. I'm not really sure about the exact source, but yeah. So you basically have this equation. You want to find like the solutions to this, and you actually have some bounds. Like you have to do this for k greater than equals to 21, which is interesting. So try the problem for a bit. Do mention any ideas you have.
We could take this mod 2.
So you want to consider the problem for k equals 2?
No, as in mod 2.
Okay, mod 2. Okay, mod, sure.
So if there's an odd number of even, it has to be an even number of even AKs, I think. No, that would help. No, sorry.
It's okay. Okay, so I will just give you a bit of a hint. Not really, it's not really even a hint, but yeah. So 2021 essentially exists because it's probably the year of the. It's probably, yeah, the year the problem was in a contest. So these constants don't really matter that much. Also, they don't matter that much. Probably matter a bit. How about using QMGM inequality somehow? Okay, so you want to use the QMGM inequality. So you would have something like this. How would how would that help? Also, yes, the thing I said about the constant, I was essentially suggesting you to try the thing for smaller values, like even k equals 2 or something. Just try out, like what happens then.
My naturals is zero allowed in this?
Oh no. I mean, in that case, you would have a trivial solution 0, comma 0. But yeah, it's not good. But it doesn't really matter, does it? You would just have one more solution. And it's quite a humble number compared to 2 to the power 2021.
Well, for 2, k equals 2, this just has one solution, I think. That is, a a1 is 1 and a2 is also 1.
Okay, so you're claiming that just like the only solution.
Yeah.
And
For k equals to 2, there will be no solution actually.
you're right.
This would not satisfy.
2 doesn't take.
Right.
Yeah.
I'm sorry.
I actually believed you there. I actually believed you there.
I'm
That,
sorry.
but yeah, happens. So it has no solutions. And it's probably not that hard to like. Yeah, that should be a number based equations. Yeah, I mean inequality. Yeah, like inequality or some inequality should just be. But what I want you to notice is that here, what were we doing here? We were replacing something with something, right? And creating new solutions. So suppose you had Manisto the liar. Absolutely. Or is he the liar? It's he's lying for k equals 2. He never said that this is true for k greater than equals to 21. Like k equals 2. It might be true for larger values. You never know. Okay. So suppose a1 comma a2 was a solution. Now can you find another solution stemming from this?
KA1 and KA2.
Sorry?
KA1 and KA2.
Okay, ka1 and ka2. You're basically scaling it. But yeah, like scaling works. But does that necessarily help? Also, here one might think that you can scale in case of like larger values as well. Actually, you can't do that because if you scale for like larger values, you would have like a k to the like I don't know. If you have a constant d, then you would have a d to the power k this side, and you would have like d square this side, which is like bad. So just highlighting one potential fake solvish trap. I don't know. So this
A1 by 2 comma A2 by 2 would be a solution because both A1 A2 should be even.
yes, but a1 okay, sure, I get. But this is essentially the same as scaling, right? You are multiplying it.
Yeah.
That isn't that helpful. Like, suppose there's like the minimum solution.
A2 comma A1.
A2 comma A1 works, right? Because it's symmetric. But I wanted to think something more useful that helps us do some infinite descent.
So maybe like earlier we can say that A2 divides A1 and then go ahead from there.
Okay. I see. But that would again essentially be similar to scaling, right?
A1 in
Yeah.
terms of A2, then your solution. Then writing the solution.
Okay. Let's just try. It's okay. Suppose A1 is greater than A2. Okay, so it's clear that it doesn't have a solution when A1 equals A2, right? Because
Yeah.
it's on naturals. So suppose A1 greater than A2, and that means that A2 divides A1, I think. Does, right? Hope it does. Wait. Does it?
I don't think so. I think A2 divides A1 square is the thing that we say, right?
Yeah.
Like not necessarily A1.
Yeah, exactly. So you can't really do that, unfortunately.
Yeah.
I think we can. So if A2 is greater than A1 and A2 divides A1 squared, then we can take A1 comma A1 squared by A2.
Okay, wait. Can you just reiterate what you said? You have A2 greater than A1?
And A2 divides A1 squared.
Right.
So if we have that, then we can take A1 squared by A2 and A1.
I'm going to take A1 square by A2 and A1.
Yes. Wait, that doesn't work at all, does it?
It I don't think it works.
I think in some cases, taking A1 plus A2 and A2 will work.
Okay. So
Or
you were
A1 plus
suggesting,
K, some constant.
okay, you were suggesting that A1 plus A2, and you want to fix the other one? Um, can
We
you
can prove
go on?
that A1 square plus A2 square is always greater than A1, A2, so we don't have a solution.
Yeah, I get that. But what we're trying to do right now is find another pair from A1, A2, which will be useful in our descent.
I think if uh, there is some uh, natural number m such that m into 2a1 plus m equals to a2 multiplied by on and on up to ak.
Okay, are you trying for the general thing? Can you just type what you said?
Yeah.
I wasn't able to follow.
Uh, in a1 a1 plus m constant.
Okay, you were adding a constant like A1 plus M. I'm sorry, your voice is not super clear right now. Could you just type in the chat?
So it will L by m into 2a1 plus m.
I'm so sorry. Could you just type the thing in the chat? That would be easier.
Like, I'm curious, do we need to make a substitution like the previous problem to make this work?
Yes.
Okay.
LHS will increase by M times 2A1 plus M. Uh, but how exactly will it increase? Okay, I get you. Okay, sure. You are adding by M. Like you are adding a constant M. Okay. LHS will increase by this, right? Okay, so let's just try what he said. Um, and RHS by M1. No, for now we are just looking at K equals 2. So you don't need to like consider. Um, yeah, so A1 plus M A2. And this is quite huge. And you had A1 square plus A2 square is A1 A2. Yeah. You have a few unwanted terms. Maybe you could make a similar substitution, like very similar to this, and get rid of all of this. Why not subtracting 2A1 A2 from both sides? Okay, I see. Yeah, I mean, I get what you were saying, but we are trying to, like, that works. That does work. You would have perfect square on one side and you will have a negative number on that side. But what we are trying to do right now is we are assuming we have a pair there, like pair A1 comma A2, and we are trying to force another pair. Like, we are trying to prove this with an infinite decent argument because you can't like do this for larger values of t. So we are trying to generalize our approach from a basis. You all are very close to the right substitution. Like A1 plus like M comma A2 was like very close. Like suppose if you had like A2 instead of like M, right? And you subbed A1 plus A2 comma A2. Then you would have A1 A2 plus um yeah. So you would instead have this, and this would be what? A2 square plus A1 A2. And this is like much nicer, right? But this is like a bit too huge. But it still differs by only two, like two A1 A2. So what is a very small adjustment you can make here that fixes this?
Maybe you could put A2 as A1 minus A2 or A2 minus A1.
Okay, let's see what happens. Um, so like yeah, it's essentially the same thing to sub A1 as A1 minus A2. Yeah. So what happens is A1 minus A2 square plus A2 square is right. A1 minus A2 instead of A1 plus A2. You would have this. How do you add subtract stuff? Yeah. 2 minus A2 square. I think down.
Actually, I was saying A1 plus A2, A1 minus A2.
Ah, okay. Okay, we can try that as well. Let's first try this. Is that okay?
Yes.
Yeah, sure. Uh, yeah, you have this, and A1 plus A square is what? A1, A2. And this is in fact A2 square minus A1, A2, which is just a negative. So you could instead do A2 minus, wait, yeah, you can instead just do A2 minus A1 comma A2, and this actually works. So if you had A1 comma A2, then A2 minus A1 comma A2 works. And since Bhairav said that we should try A1 plus A2, A1 minus A2, we will do that as well. Because why not? Yeah. Time. Let's just try this. This and we have what's on the other side. But sorry, A1 square minus A2 square. But yeah, these are clearly not equal, right? Because this is like much bigger. It's like 2 times A1 square. Anik says in general, M equals A2 time till AK minus 2 A1. Okay. Yeah, good. Like you're very close to it. So for K equals to, you have this. But actually, you can't necessarily do an infinite decent yet. Because if you apply this step again, you will get back to A1 comma A2. So you don't really have an infinite descent. So now it's finally starting to make sense why like it was for large enough k.
Yes.
Right. Now, as Anik mentions, you can okay. But why should there be a constant of two then? Like I get that this is like natural to consider a1 as product a j 2 a minus a1 because there's sort of what we did here. But why a constant of two? I don't think you need the constant. Can someone check? Okay, so like for general k, what we're doing is you have you're assuming you have a tuple a1 del ak, and as Anik said, you are going to consider a2 till like this quantity. Let's call this m, and this works. Can someone check if this works?
In this we replace a1 by n.
Yeah, m is this quantity, which is similarly defined as a1 minus a2 because yeah. And this is sort of natural to define this. Um, yeah, like we saw a1 minus a2 works, and the idea is basically want to see how you can do similar stuff for larger values. Yeah, this is like very natural thing to consider. Is that clear to everyone?
Yeah.
Okay. So can you do an infinite descent now? Because note that when you consider the case of k equals 2, right? The sum of like this quantity is sort of not very well defined. As in, you can't really tell if this is bigger or this is bigger, right? But here you can kind of do this because this quantity is very huge. And you can essentially assume that um yeah, you can assume that these are this is like the order, right? Because the thing is like completely symmetric. So you will have that this quantity, which is m, is in fact larger than like all of these. like A1. Does that make sense?
Yes.
Yeah.
And you can do the same thing for this pair, like this tuple. And you can just go on for a. You will have infinitely many solutions. Is this clear?
Yes.
Everyone?
Yes.
Yes.
So, getting back to the question, claims that can find at most 2 to the power 2020 solutions. Well, 2000, 2 to the power 2021 is the most random thing ever. It basically is sort of saying, can you like find finite? Yes, he's necessarily lying. So yes, this okay. I'll just summarize what we did. Right, we tried the case for k equals to, even though you had in the problem that k is always greater than or equals to 221, you still tried that defying all odds because you are super cool, and you realize that you can replace a1 by a2 minus a1 and it still works, which is very cool. And in if I was like, if this problem wasn't some contest, I would be trying even k equals 3, even probably trying k equals 4. Because um, considering this quantity is not immediately like obvious. Like,
Yeah, noticing the general pattern might be helpful.
exactly. So if you like, you could probably be working with k equals 3 and okay, wow, a1, a2 minus a3 works. That is
I
great.
have a doubt regarding this question.
Sure, go on.
We proved that if there exists a solution like A1, A2, AK, there exists infinitely many solution, but we did not prove there exists a solution in the first place.
Right. That is a very valid doubt. Okay, that's actually very valid. Okay, I saw that Bhairav raised his hand. Just give me 1 minute. I will come back to you. Um, yeah. So we haven't really proved that there is a template, but we proved that if there is one, there are infinitely many of them, right? So can you even find a tuple? Like, what do you think? They just try to find the small construction. It's actually very hard, right?
Yeah, nothing like A1, A2, 1 does work actually in this case. Actually, for k equals to 3, it is very hard to prove.
Yeah. Okay, wait. We need to find an initial solution, right? Let's start. Um, right now I'm with you. We are solving the thing together. Let's go. So you want to find an initial solution?
You said M was not necessarily true for k is equal to 3, k is equal to 4. So what did we find that
So large enough it might exist. Exactly.
is wrong?
Sorry. Wait. Are we sure that? Are we sure? What Finical? Okay. Are we sure Finical is not lying as well? Hmm. I don't think she's lying. Hopefully. Okay, that's interesting. Shouldn't be hard. Wait. Okay, it's actually very hard to find a construction, but yeah. So I'm sorry. I should have explained to it you like I should have explained you this a bit earlier, but he like the question does is he necessarily lying? So it's like probably very hard to determine a construction for some value because it says for some k, right? It can be anything and
Yeah.
clearly very general construction of this mixes. So he's not necessarily lying. So yeah, but yeah, you if you have one, you can generate an infinitely many solution. Is the idea clear?
Yes.
Also, Bhairav raised his hand a bit back. So yeah, what was the question?
I was just going to ask about that.
Okay, I see. Yeah, I'm actually very sorry that I didn't explain to you a bit earlier, but yeah, I'm sorry. So yeah, I will just summarize the thing once again. The question is sort of tricky. It asks if he's necessarily lying. So the word necessarily holds a lot of essence here. So essentially, if we try the problem for k equals 2, we see the general pattern for like after working with maybe k equals 3 as well. We didn't really look at k equals 3 here because our friend Anik suggested that we can consider this magical quantity, which is not very magical if you have tried some examples. And you see that for large enough stuff, this quantity is actually very huge. So you can transform your initial tuple to another one and so on. You have huge numbers and you will have infinity many solutions. But it is very hard to determine an initial construction. So it's not necessarily lying, but yeah, you never know. So yeah, everything is clear. If there is any confusion, feel free to ask.
If you use PMI to prove that it is true for even square till AK square is equal to A1 into A2 into AK, then we find that A1 square plus AK square plus A square K plus 1 is equal to A1 A2 A2 AK plus 1.
I
So
don't
can
think.
we write
Yeah, go on.
so can we write that A square K plus 1 is equal to A1 till AK multiplied by 1 minus AK plus 1. So every if AK plus 1 is A square AK plus 1 is of the form like that, so it will have a solution.
Yeah, but in general, I don't think you can induct here because there's like very, yeah, I don't think you can induct. First of all, you don't even have a base case,
Wondering.
right? So the fact that it will be just true for after some n, like large enough, is very sketchy. I don't think it's true.
Wait, so what we did was that for some k there might not be a solution, hence is not necessarily
Yeah, yeah.
right.
Some K, then simply
Yeah.
might.
So what? So what was the point of all that infiniteness? You can just take that point. Like for some k there might not be a solution, hence is not necessarily because on that particular solution clearly less than.
I'm sorry, I really couldn't.
Yeah, like what I meant was for some k there might not be any solutions. So zero is clearly less than this enormously large number. So we don't really have to do the infinite descent either.
You have to. The point of the infinite descent is that like finite barrier.
What?
Like Finnegan claims that Manisto claims that Fenical can find at most 2 to the power 2021, and there's a
Yeah.
final number essentially, right?
Huh.
Yeah.
Yes.
Oh, that's the point. In case you have an initial construction, you will have infinitely many. It like
Yeah, and in case if we don't have an initial construction, we won't. So we won't even need a
but it does say that
because sir,
find the solution to the equation in natural for some
uh, oh okay.
for
But
some.
still, like our entire oh, uh,
Is that clear? Or do you have?
yeah.
Okay. If you still have any doubts, feel free to like tell me in the chat maybe, because yeah, I will have to move on to some Vieta jumping, because yeah, I have been clickbaiting people that we are gonna do Vieta jumping and stuff. So yeah, Vieta jumping. Guess what happens when you hear this magical phrase? A problem gets summoned. Which problem gets summoned? Does anyone have any guesses?
1984
1988 P6 IMO.
Yes,
Yeah.
literally every class ever in the history of Olympiad math has had this problem, like in an infinite descent and theater
And
jump.
I think this problem uses both the concepts, like both infinite descent and Vieta jumping. Yeah, so it's very
Vieta
relevant here.
jumping is basic. Vieta jumping is basic.
Yeah, they go hand in hand. It's
Yeah.
really different. Yes, so in fact, this problem does have a stronger form. We can prove that there's always like the GCD of this square. Okay, how many of you have seen this problem before? Raise your hand.
I have.
Even
Yeah, I have seen.
Okay, a lot of people have seen this. Okay, how many people have seen this but don't know how, like, the solution? Wow. Okay. Well, that's great. A lot of people actually know it. So, yes. I was actually quite worried that everyone has seen this. Bro, are you really going to do this problem in a class in 2024? Come on. It's like, no. We will do it. We will still do it. But yeah, this was a very interesting story. Terence Tao, who is probably one of the greatest mathematical minds of our generation, didn't solve this at IMO, so people are hyping it. So yes, I'm hyping it as well. Very cool statement as well. If a square plus b square by ab plus 1 is integer, then it's a perfect square. So I won't really, okay, yeah, sure. Just think about this problem for a few minutes, like what are potentially the solutions and everything, and I'll come back to you. Are we doing this question for the 10th time now? Even at Remote Easy in West Bengal, we did this question. Yeah, that makes sense. But yeah, it's still like a very great problem if you want to introduce Vieta something to someone. I wonder if this problem will be relevant like 50 years from now. Maybe it will because of the lore. People like gossip and lores. Yeah. Okay, now I'm realizing that I have probably scared a few people because I said some very strong people didn't solve this encounters. But yeah, don't worry. That was 1988. We are in 2024. We are so much stronger now. And you know infinite peace. And I don't really expect you to solve this right now. But yeah, I just want you to be like, how might you?
We also have the solution.
Do you what? I'm sorry.
Oh, I was just saying we also have the
Like the solution set.
yeah, we have the solution, so we can like, Google it.
I mean, that would be great. Okay, so what works? 1 comma 1 works. Does it? It does.
Yes.
Else
Yes.
what? Come on, we need some more pairs.
Come on, two. No,
Two.
wait, that doesn't work. That doesn't work. Two, come on. No.
Does it work? I don't think so.
Comma 0.
Doesn't. Positive integers, I think. It's specified.
Maybe the solution set is 1 comma 1.
It's not sadly.
I think we will get infinitely many solutions for it.
You will, but like just let's just like try to find some smaller ones. Because why not? That's something you should be doing for like any diaphantom equation. 2,8 works. Or does it?
I
Now,
think so.
Yes.
does they go?
Mhm.
That
And I
means
think 3,27 works as well.
that's huge, right? 3,27, 729 plus 9, 7,
9,729.
738 plus.
Just like A comma AQ works because
Yeah, true.
A to the
A
power
comma
4
AQ.
plus 1 will be cancelled.
Right.
A comma AQ works.
A comma
Yeah. Hmm.
A cube comma A works. How non-trivial. Oh my god. Yeah. So you have infinitely many solutions. Pyrup has been disproven. Okay. Without wasting too much time, I will just elaborate what we are going to do. So essentially the idea is suppose a square plus b squared by ab plus 1 is k.
We can write a function about A with B and K.
Okay. Right. You have this and you are trying to define f of, I don't know, x. Not x. I don't like x. Let's go t. I actually have seen people define it as f of t a lot of other places. So I'm doing it here as well. I don't know why. I think people like it for some reason. So you have this. You have a quadratic. So we define this function, and there's a quadratic. And a quadratic equation has two roots. One of the roots of this equation is a, and other one is probably, let's say it's x. That's the great part, that's why I picked t, because I wouldn't want to like work with t for the rest of the thing, because yeah, this is a random value, no one knows. Yeah, whatever. Anyways, and by and Vieta's relations were prerequisite for this class, and there's a plus x is kb, and ax is b square minus b. What this essentially means is that x is also an integer. Do you see why?
Because KB is an integer and A is also an integer.
Right. And you can write x as b square minus kb. So you had a pair a comma b, so it's like that word, and from there you went to b square minus k by a comma b. Now what do we want?
I want the second pair to be smaller.
Right. You want the second part to be smaller. Okay, what happens if it's like bigger than?
B squared minus K is greater than A squared. So then we just take that A is greater than B.
Okay. So wait a second. Okay. So um yeah, makes sense. So you want this to be smaller than this. I mean A, right?
Yeah.
Why do you want that?
To get the area of the infinite descent, I guess.
Right. Okay. What happens if you apply the thing again? Like the same thing. Do you get a decent? Like now this time say this like A dash. and this is not given. This is like
We
x.
we can say that like a dash is less than a,
Okay. Why is that?
and it, because b square minus we can assume that without loss of generality a is greater than equal to b,
Okay. You are assuming a is greater than b.
and b square minus k by a is less than b square by a, which should be less than a.
Less than b square by a, which should be less than a. Which should be less than a. I'm sorry. Messing up. Oh. Okay.
So like a dash is less than a, and
Yeah.
we can say like a plus b is greater than
A plus B greater than A dashed plus B. So the sum keeps on decreasing, like sum of the, you know.
Sure. But
Yeah.
how are you continuing from here? Because if you like do the same operation again, you have the
I
same.
think we get back to A and B again.
You get back to a comma b. So
Yeah.
how infinity?
but we did like ax is equal to b square minus k, and we assume that k is not equal to b square. Hence, we can do that x is no positive integer, because x could be like 0. So like if k is not equal to b square, then a dash plus b is less than a plus b, and we could do the same thing forever. And because uh, it would go like to 0, so that would not conclude. So k has to be equal to b square.
Okay. So if you had k is b square, you are done. Right? So assuming it's,
Yeah.
but yeah, that still doesn't answer my question though. Like how exactly like are you going to perform this thing over and over again? Like let's
Or
just
I
we
think
had
we can
2,8. Yeah, go on.
I think we can assume that uh, AB is the solution with the minimum sum A plus B.
Right. That works. There. If a plus b is the minimum, you just found x comma b, which has an even smaller x plus b, which is a contradiction, right?
Contradiction.
Right. Yes, that absolutely works. That is a very neat way to finish the thing. But what I wanted to talk about is that you can't really do the operation. What you said absolutely works, but I'm just reiterating on another thing that you can't be just plugging in this again because then you get back to a comma b, which is bad. So what you have
Yeah.
to do is you have to switch up. Notice that if b square minus k by a comma b works,
Then B comma B square minus K by A also works.
right. Now you do the same thing. You have a,
Yeah, and we get the descent.
yeah. Does that make sense?
Yeah.
Okay, let's just try one, I don't know, random pair. 2 comma 8. Where does it work?
64 minus K by 2 comma 8. Yes.
64 minus.
B square minus K. B square is 64.
I can't math.
You would get like 0, 2, I think.
I think then it becomes hmm,
I'm so bad at math.
You will get 0, 2.
you
Yeah,
get
we just need to
plus-
switch this. 8
no,
comma 2.
it'll actually
Then, yeah.
become 34,8.
34 comma 8, right?
Yes, so if you do it the other way, you get minus 2,8.
No, like you first switch it up. Like this. Because you can't do this directly. You will end up reaching at 2 comma 8 once again.
No, as in, if we start with 2 comma 8 and then switch it and put 8 comma 2, then that becomes 8 comma minus 2.
That's not good though. Because positive integers. We don't want that, do we? Okay, yes, Raya, you raise your hand. Do you have any question?
Yeah, I mean, like, where do you get the 34,8 from?
I didn't calculate that. Okay, I will just do it. There you go. This is 68 by 17, which is 4. So k
Okay.
is 4. B square is 8 square minus 4 by 2. Isn't that 30?
That is 30.
Think
Yeah.
so. Yeah.
Okay, better. So now you're
ये देख, घर लग रहा है मुझे।
नहीं हॉस्टल लग रहा
नहीं बच्चा, वो देखना दरवाजे हैं, दूसरा कमरा भी है।
हाँ।
पानी की बोतल से कितनी?
Oh, sorry, I have to meet you. I'm sorry. Yeah, back. Anyways, 8 comma 30. And you can generate more pairs just like this, right? And a very cool,
Yeah.
if you like consider like the hyperbola made by this is actually a hyperbola, by the way. This equation. If you are a JE kid, you know that. You should probably know it otherwise as well, but yeah. So yes, this is basically an equation to a hyperbola. And here k was what? I don't know. 4. So if you plot this, I'll just open GeoGebra. Yeah, I know I'm not sharing right now. Like I'm not sharing the GeoGebra screen right now, but yeah, I will do that soon. So equations. This. Okay, so yeah, I need to switch my screen. Why is this colored though? Can you see my screen?
Yeah.
I have no idea why this is colored. I don't like colored screen. Why? Why are you doing this? Okay, it doesn't matter. So first you had the point, I don't know, 2 comma 8. The size of the hyperbola. And next you had 30 comma 8.
Yeah.
Size of the hyperbola. You also have 8 comma 30, which is somewhere around there. We don't care about it.
Try 112.
Sorry?
112.
No, I'm sorry, your voice wasn't clear. 8 comma 30. Okay, can anyone tell me what was the next point? 8 after 8 comma 30. I know it's a bad, okay, it's a really horrendous calculation. But
3 comma
Travel
27.
by the y-axis.
yeah, 3 comma 27 works, but like we want like in this sequence, in this chain, 2 comma 8, 30 comma 8.
we can travel by the y-axis.
I think the next point is 112, 30. At least I'm getting so.
112,30.
Yeah, it's working.
That's quite far away.
But yeah, if we plug in the formula b square minus k by a, so we get 112.
What do
I
you
think
have?
if you put the coordinates the other way around, you can see it's on the same line.
We have the graph, can't we see X,
You also had 8,30. Also, like 0,2 works. I know it's like we are talking about only positive integers here, but in general, 0 works, right?
Yeah,
So 2,0 works as well. So yeah, if you notice,
I can probably tell you another point that works. It's very far away, but yeah, 418, 112. That's next in the sequence that we were searching for.
400.
18, 112.
I'm sorry.
1, 1.
1,1 is not in the sequence.
Yeah.
So you basically have this bunch of parallel lines, if you see them.
Not 105, it's 112, I guess. Yeah,
Yeah, it's okay. Thank you so much.
you're welcome.
So essentially, if you started with some solution like very far away, this redirects you back close to the origin, right? You
Yeah,
go from here to here, then yeah, you go here, then like you just keep on going closer to the origin.
right.
So this geometrically makes sense as well.
Yeah.
Right. So if you still have any doubts, feel free to ask. We will do one more problem, which is also like Vieta jumping. And it is like, yeah, I will, well, it will be you who's going to do it. And I will basically be spectating, maybe. I don't know. What's the right word? Yeah, whatever. But yeah, if you have any doubts, feel free to ask. Okay, I should be sharing the one more. Five hundred and 30. Did we not try that? Yeah, we did. So it's hard for me to like keep track of that all the time. I'm sorry. But yeah, once again, any doubts? Okay, I'm assuming you all of you are. And yeah, try to prove this. Like, try to characterize all solutions. In fact, you have already done that almost. And yeah, you can prove this. That this, in fact, will always be the G, like square of the GCD. So that is a homework problem. Next up, we have an A7.
Like, I'm sorry to interrupt, but can you repeat this?
Go on.
Like, can you repeat the homework problem?
Yeah, the homework problem is basically prove that this quantity, which is always a perfect square, is in
Yeah.
fact the square of GCD of A and B.
Okay, thank you.
Okay, next up you have an A7. Yes. Can you imagine A7 in a Vieta jumping class?
What is A7?
What? As in the year of the A7?
Who is A7?
Okay, I'm actually just kidding. It's not really an A7. It's HMMT A7. So yeah.
Okay.
So basically HMMT has like algebra and number theory, like the contest has like algebra and number theory together and it's called just way. So it's like you have problems to like I don't know, A9 or A10 or something. And yeah, this was A7. So let's try this for a while and I will walk through this after a bit. Okay, I'll just help you out a bit, like just make things a bit smoother. So you can consider the quantity k equals c minus 2 instead, and that makes it a square plus b square plus a plus b by a. This is like a bit nicer. You'd probably have already seen this. Yeah. Any ideas? Any solutions?
I think.
Yeah.
No, sorry.
Like 1, 1 works, obviously, right? 1, 1.
Yeah.
You would have what, 6? Okay, so Sharanya is doing something different. They considered a plus b as x, and then you also have a quadratic. So interesting. But is like characterizing AB easy enough? Okay, what else works?
I think 1, 2 works as well.
1, 2. Okay.
And I'm not sure.
What would the value of C be? 4 times 3, 12, 6. 1 second.
6 again, yeah. I think 116 is, yeah, it's also 6. Yeah.
So we want to find all possible values of C. So yes,
Yeah.
it does occur quite a few times. We can let A equals dx and y equals dy. We would get d divides x plus y. Okay. So we have a lot of ideas coming in. B should divide A plus 1. And A should divide. Okay. Okay, give me a minute. I'll be back in a minute. Okay, I'm back. Yeah, we had a lot of ideas coming in, and they were through chat indeed. A lot of people have messaged me, so yes. So Shaddat wants to consider. Tanish wants to consider A equals dx, y equals dy, and then you have d divides x plus y. Wait, what? Why should d divide x plus y? Okay, I see. Yeah, interesting. B should divide A plus 1. A should divide B plus 1. Really? Are you sure about that? Let's try. Okay.
I think I have an idea, that is, if we consider the GCD of AB to be D, then D divides x plus y.
Yeah.
I mean, and x plus y times dx plus dy plus 1. Can we somehow proceed from that?
That's interesting. Tanishq also had this idea. So essentially, would have um, I don't know, t square x square t square y square plus dx plus dy. So, um, yeah. So indeed, you would have d divides x plus y. I'll just simplify the entire thing because why not? T x squared plus y squared plus I don't know, x plus y. X, y. Right. Yeah. D divides x plus y. Okay. Yeah. That's interesting about this. But yeah, I want you to like focus on other solutions. Like you had 116, 126. Can you find other ones? So 235 works. Does it? 5 and 6. 6 times 5, 30, 30 by 6, right? Yeah. Also, 2 comma 2 comma 5 also works.
Yeah, it does work.
Okay, right. So if you go on exploring a little bit more, you'll see that you always have 6 and 5. So it's probably safe to think that the only possible values of C are 5 and 6.
I have solution, I think.
Okay, great.
Should I say it?
Yeah, feel free.
So what I did was like the before question, a square plus b square plus a plus b is equal to kab.
Right.
So a square minus kb plus a plus b square plus b equals to 0. And a is already a root. So we say the other root is alpha, or let's say x, anything.
Okay, wait. So you have this thing, which is like I don't know, t kp minus 1. Am I right?
Yeah,
And you have no.
b square plus b.
Now alpha is a is a root. You have another thing
And other root is x.
x variable.
So a plus x equals to kb minus 1.
This x is kb minus 1, so x is an integer.
Yeah. And x should be like b square plus b by a.
X will be b square plus b by k.
I think a plus x is 1 minus kb.
Actually, ft should be t square plus t square minus t into kb minus
Yeah,
1.
actually right, yeah.
My bad.
X is equal to b square plus b by a.
Yeah, x equals to b square plus b by a.
Sorry, I'm sorry. Yes, I'm the guy who.
We say
Yeah, go on.
that a is greater than equal to b.
Okay.
Without loss of generality. Now we take two cases. If a is greater than equal to b plus 1.
Okay. If a is greater than equals b plus.
If a is greater than equal to b plus 1.
Right.
Then x should be less than a.
Yes, a should be less than. Yeah. Like.
And we say that a plus b is minimum, just like the before.
Okay. So you went from a comma b.
So a equals to
b square plus b by a b, like b square plus b by a comma b. Right.
And we say that a plus b is minimum.
You are assuming a plus b is minimum.
So because a dash because x is less than a, so it violates the minimality. So a has to be equal to b.
X is less than a. Why?
We can just show that x equals to b square plus b by a, and if a is greater than equal to b plus 1, x should be less than b, and we say that a is greater than equal to b, so x should be less than a.
Okay, let's just formally do this, right? So you have b square plus b by a.
Because a is greater than equal to b plus 1, this should be less than equal to b.
Okay. Yeah.
Should less than equal to.
Yeah.
And we assume that a is greater than equal to b.
Yeah. You're basically done.
Yeah. So we say that a equals to b has to be the minimum, and we can check putting A equals to B. We can see like 1, 1 and 2, 2 only works. And for those two cases, C equals to 5 equals to this. C equals to 5 or C equals to 6.
Yeah, so this means that, okay, so you assumed A plus B is minimum. Then you went for this argument. You have a descent. And this means that A has to be B, like A equals B. And if A equals B, wait, did we mess up? Because we had 2 comma 3, 1 comma 2.
Yeah, we
Right.
actually set for the minimality. 2,
Yeah.
3 is not the minimality.
Right. So now if A equals B, you will have 1 comma 1 and 2 comma 2. And this is easy to prove. Like you can just plug in stuff. Like, I will still do it because yeah, you would have 2A times 2A plus 1 dividing A square, right? Yeah. Which means 2 times 2A plus 1 divides A. Yeah, A has to be 1 or 2. So now from this, you can actually characterize all solutions. But yeah, before that, is everything we did now clear to everyone?
Yeah.
If you are unable to speak, then please at least raise your hand.
Yes.
Like if it's clear, then raise your hand, not otherwise. Yeah,
Can you please summarize after the step of without loss of generality?
yeah, I will summarize the thing, entire thing. Don't worry. Okay, we have quite a few people raising their hands. Great. I will just summarize the entire argument that just happened. This is very similar to the previous problem. So first of all, we subtracted 2 to make this statement a bit simpler. You can do this. You can do the problem even without this, but it just makes it neater. Nothing else. So we saw that these are some solutions, and 6 and 5 are the only ones that work. Now, like the previous problem, we assume that yeah, like some A comma B works, and you have a K that works, and you define this function, which is also a standard, I don't know, Vieta jumping equation or something. I don't know. Yeah, we did something very similar in the last problem as well. And next you had this, you have another root with A that is also an integer, and this B squared plus B by A. Now, without the loss of generality, we are assuming A greater than equals B. You can do that because there's like symmetry, right? It's completely symmetric. A plus B, A plus B, A B.
Yeah.
So it doesn't really matter if you assume that A is greater than equals to B. Now, what Aritra does is that he takes 2 cases. Since A greater than equals B, he first takes the case of A equals. He first takes this case, but let me just summarize it differently. So first he looks at A equals, what happens when A equals B? When A is equal to B, you would have this. And this means that A divides like this thing. Which means obviously this works for 1 and 2, but for larger values these are clearly co-prime. So it doesn't work. So A equals 1 and 2 are the only thing. So yeah.
C equals 5 and 6 are the only values.
We haven't proved that yet. Like we assume we are just looking at the case where A equals B. Next up, you'll look at the case where A is not equal to. And A not equal to B also means that A greater than equals B plus 1. Because you assume without the loss of generality that A greater than equals B, which means A greater than B, right? And similar to the previous problem, you want that this is smaller than A, because then you have a descent and you are done because you assume A plus B is minimal. And proving that B square plus B by A is smaller than B is actually not that hard, because there's B times B plus 1 by A and B plus 1 like, yeah, B plus 1 is greater than, less than equals to A. So there's just, does that make sense?
Yeah.
Does the entire argument make sense to everyone? Right. Okay. And from here, you can actually characterize like all solutions. If you have like 1 comma 1, you would end up like at 2 comma 1. But if you do the operation at 2 comma 1 again, you will get to 1 comma 1. There's a common trap we noticed in like the previous problem as well. So you go for 1 comma 2 instead. And then what is the next? What is the next number? 1 comma 2, you have 6 comma 2. And 6 comma 2, if you apply the operation again, you would have 1 comma 2 again, so you can't do that. So you actually take 2 comma 6. And this is like sort of like a binary tree. Sort of. You'll have stuff going on. So yeah, it was pretty nice. Similarly, you can do the same thing for 2 comma 2 and get this sort of binary tree. So yeah, looking at these structures is sometimes also very important, like the solution set structures. For example, here it is a very nice one. And yeah, this might help quite a lot. So yes, that was the last problem of the class. If you have any doubts, feel free to ask. Any questions, not just related to Vieta jumping or something, like in general, if you have any questions. What if A is not equals B? Yes, if A is not equal to B, then as we assume that without the loss of generality, A greater than equals B, which means A greater than equals B plus 1. Because we are disregarding the equality case from here, because we already considered this, which is equivalent to A greater than B. Is that clear?
Yes.
Yeah, great. Any more questions? You can ask quite literally anything. Yeah, thank you so much for attending. Okay, I'm assuming no, people don't really have any questions. Vieta jumper just play with the quadratic? Yeah, pretty much. I think Vieta jump is just fancy way to say infinite descent with quadratic stuff. Yeah, it's just like just a fancy name. It's nothing like super high tech number theory. But it's very clean. You get very nice structures. As we saw, we had the hyperbola. We had like very nice directing arrows, and you would eventually reach to the origin. And here we had a binary tree sort of structure. So yeah, it's pretty cool. So okay, yeah, I think we can stop recording now. If people don't have any questions.
Thank you so much, Debayu. This was a wonderful class. I'm sure everybody enjoyed the lab.
Thank you for inviting me. Such a pleasure.